Hi everyone, in this video we are going to talk about NP-completeness. Now this is the second video in this two-part series, so if you have not watched the first video, I recommend that you watch that video before watching this one. Now in this particular video we are going to prove that the CLIQUE problem is NP-complete. So to prove that a problem is NP-complete, we have to do two things. So let's just recollect what we have to do to prove that a problem L is NP-complete. The first thing that we have to do is we have to show that L is an element of NP, or that L lies in NP. Then we have to pick some well-known NP-complete problem, say L prime, and we have to reduce L prime to L. Okay, this is very important. Note that you have to reduce L prime to L and not the other way around. Okay. Another very important thing to know about NP-complete problems is that both L and L prime are decision problems. They are not optimization problems, they are both decision versions of the problem. Now, if you don't know what is a decision problem, I discussed this in the earlier video in this playlist. Now, to prove that the CLIQUE problem is NP-complete, what we are going to do is we are going to take a well-known NP-complete problem, that is 3CNF SAT. Now we are going to take 3CNF SAT and reduce that to CLIQUE to prove that CLIQUE is NP-complete. So that's what we are going to do here. So to recall what 3CNF SAT is, 3CNF SAT is basically Boolean satisfiability. So we have a Boolean formula phi here, and that is written in this conjunctive normal form where all the literals within a particular clause are odd and the clauses themselves are ANDed, as we can see here. So the clauses themselves are ANDed. Okay. Now, x1, x2, x3, x4, x5, these are the literals, and an assignment of these literals such that phi evaluates to true is what is 3CNF satisfiability. So in 3CNF satisfiability, we have these literals because it is 3CNF. Within each clause, we have three literals. And the goal is to find an assignment of literals such that phi evaluates to true. So now that we have recollected what 3CNF SAT is, let's try to find the decision version of this 3CNF SAT problem. So in the decision version of the problem, we are going to answer yes or no question. The question that we are going to answer is there an assignment of literals such that phi is satisfiable? The goal here is not to find that particular assignment. In the decision version of the problem, we're just answering the question if there exists an assignment of these literals such that phi is satisfiable. So it's a much simpler question that we're trying to answer rather than solving the question itself. Okay. So this is our well-known NP-complete problem, particularly L prime. Okay. So that's what the 3CNF SAT is. Now, let's get to CLIQUE. So CLIQUE is the problem that we want to show is NP-complete. Okay. So let's first try to understand what CLIQUE is. A CLIQUE in an undirected graph. Okay. So in the graph we represent it with V comma E, V vertices and E edges. A CLIQUE is a subset V prime of these vertices. Okay. And each pair of vertices in V prime is connected to each other. Okay. So it's a complete graph. This V prime is a complete graph. Okay. All vertices in V prime are connected to each other. Now the size of the CLIQUE is a number of vertices in it. Okay. So if V prime is say 5, the size of the CLIQUE is 5. So let's try to understand this with this example here. So here A, B, C, D in the first is all vertices are connected to all other vertices directly. So there's, for example, let's consider A. A is directly connected to B, C, and D. Similarly, B is directly connected to A, C, and D. The same holds true for C and D. So this particular example here is a CLIQUE. Now let's look at the example on your right. Let's see that A and C are not connected to each other. Therefore, A, B, C, D do not form a CLIQUE. Okay? But if you look at, say, A, B, D here, A, B and D together form a clique because they're connected to each other. Okay, so in this particular case, A, B, C, D together don't form a clique, but we can say that A, B, D alone form a clique. So clique in an undirected graph is a subset of vertices such that each pair of vertices is connected to each other with an edge. Okay. So what is the optimization version of the clique problem? In a clique problem, the optimization version is finding the clique of maximum size in a graph. So you're presented with a graph G, and the goal is to find the clique of maximum size that is present in this particular graph G. So that is the optimization version of the problem. Let's look at the decision version of clique. The decision version is much simpler. The question that we are asking is, does a clique of size k exist in this graph? So you're given a graph, and the question that we're asking is, does a clique of size k? So the k could be anything like, does a clique of size 5 exist in this graph? Does a clique of size 10 exist in this graph? That's the question that we are trying to answer. And once again, note that we are not trying to find a clique of size k. We are just answering whether it exists or not. So it's a yes or no answer. Okay. So the formal way of defining it is in this way. So clique G comma K. G is the graph containing a clique of size K. Okay. That's the formal way of defining this decision version of this clique problem. So what have we looked at so far? We looked at 3CN of SAT, which was our known NP-complete problem, and we talked about clique. And we want to show that clique is NP-complete. So we looked at the two decision versions, and to show that clique is NP-complete, first we have to show that the clique problem, the decision version of the problem, lies in NP, and we have to reduce 3CN of SAT to clique. Okay, so let's go about proving that clique is NP-complete. Now before doing that, let's try to solve this problem. Okay, let's take a moment to see how we could possibly solve the clique problem. Now, say if you want to find out a clique of size k in a graph, okay, how would you go about finding a size of clique k? So what you could do is you can list all k subsets of V. Like you can figure out how many k subsets of V exist. Okay, so you could group first k vertices together, that's one group. And then there are another set of k vertices, that's another group. And you could go on, so on and so forth, and you will find all these subsets. Then you can check each of these subsets to figure out if any one of them is a clique. Now, how do you check if a subset of vertices form a clique? You check if each vertex, if each pair of vertices in this subset is connected by an edge. If each pair of vertices in the subset, in a particular subset, are connected by an edge, then that subset is a clique. Okay? So this is a brute force approach to actually figuring out if there is a cake-sized clique in a graph V and what is that particular clique. So you could answer it this way. Now, this is a brute force approach and it solves our problem, but this problem is not polynomial in time. To find out the solution, you have to spend super polynomial time. So this is not a polynomial solution. And it does not appear that this problem will have a polynomial time solution. So though we have solved the clique problem, we don't have a polynomial time solution. So the goal is to prove that the clique problem is hard. Okay, and it can only be, the solutions that exist are not in polynomial time. Okay, so now to do that, we get to our formal proof. That is, the clique problem is NP-complete. So the first step is to show that clique is an element, NP. So clique is an element of NP. So to do that, what do we have to do? Now, if you've given a certificate, we need to be able to verify the certificate in polynomial time. That's what being in NP means. Once again, if you're not familiar with this concept, there's earlier videos in this playlist which describe what P and NP are. I'm going to assume that folks who are watching this video have already gone through those videos here. So to prove that clique is an NP, what we have to do is we'll be given a certificate and we'll have to be able to verify the certificate in polynomial time. Now, given a certificate, we can check if the certificate is correct. That is, it is going to give us a clique by verifying if each pair of vertices U and V in the certificate, there exists an edge. if for each pair of vertices u and v there exists an edge, that means that the certificate is actually true. So we can easily verify this in polynomial time. You just look at all pairs of vertices and see if an edge exists between them. Okay, so this can be verified in polynomial time. Now the next part is the more difficult part of any NP-completeness proof. Now we have to prove reduction. So what we are going to do is, first we are going to take 3CN of SAT and reduce it to CLIQUE. That's what we are going to do. Now the first thing that most students face here is 3CN of SAT is a Boolean satisfiability problem. CLIQUE is a graph problem. Apparently they have no connection between them. And that is where proving NP-completeness becomes hard. But to prove NP-completeness, it is not necessary that both these problems are in the same domain. So for 3CN SAT, it's a Boolean satisfiability problem. CLIQUE is a graph problem. What we could abstract these details away, and we'll see how we can actually prove NP-completeness. So if you've never seen proof of NP-completeness before, you might find this really interesting. So to prove that we can reduce 3CN of SAT to CLIQUE, what we do is we start off with an instance of 3CN of SAT. Okay, that's what we're going to do. We're going to start off with an instance of 3CN of SAT. Okay, now let us assume that the Boolean formula phi here for this instance has k clauses in it. Okay, and that Boolean formula is expressed in this particular way, that C1 and C2 and C3 so on and so forth up to Ck. So there are k clauses. Now each clause is going to contain 3 literals. So if you're considering the rth clause CR, it will contain 3 literals, L1R, L2R and L3R. Okay, so that's the definition, and that's how we are looking at one instance of 3CN of SAT. The next approach is to construct a graph G such that phi is satisfiable if and only if G has a clique of size k. Now this is where the art part of it comes in. Now how do you do this kind of mapping? The only way to know how to do this kind of mapping efficiently to prove NP-completeness is to practice. So when you look at this for the first time, you might figure out how do I do this myself? All that I can say is this is an art, and more you spend trying to prove NP-completeness, you will get the hang of it. So what we're going to do is we're going to construct a graph G such that phi is satisfiable if and only if G has a clique of size k. Now notice the if and only if. The if and only if means that we have to show the reduction both ways. So we have to show that if phi is satisfiable, G has a clique of size k. And we have to also show the other way, that G has a clique of size k, that means phi is satisfiable. Okay, we have to do this. Okay, so first, now we have to construct a graph G. So what we have is we've taken a general instance of 3CN of SAT. Now we have to construct an instance of CLIQUE, and we have to somehow map the instance of 3CN of SAT to the CLIQUE. Okay, so to do that, what we first need to do is we have to construct the graph. Now constructing the graph is left to us. We could construct the graph the way we want to, because we are trying to prove this kind of mapping. So that is the tricky part here. So we notice that for each clause, okay, there are 3 literals in each clause. And say, if you consider clause CR, it has 3 literals, L1R, L2R and L3R. Now, for each of these literals, we are going to draw a vertex in the graph. Okay, so we'll have vertices V1R, V2R and V3R corresponding to L1R, L2R and L3R. Okay, so we are going to create this. Now how do we construct this graph? So we'll show this via an example. Okay, now let's consider that phi is this particular formula here. I'm just going to choose this. So phi is this particular formula right here. That's the phi. Okay, so if you look at C1, we will draw 3 vertices, x1, negation of x2 and negation of x3. Similarly for C2, we have negation of x1, x2 and x3. For C3, we have x1, x2 and x3. Okay. Now, once we have drawn these three groups of vertices, we are going to connect them. Now, you can notice that there are no edges between the same group. So in this group, there are no edges between them. Okay, for x1, negation is not connected to x2, and neither is it connected to x3, and so on and so forth. So within a group, there are no connections. Now, you're going to draw edges from one group to the other group. Now, the way you're going to draw an edge is there's going to be no edge between a literal and its negation. Okay, so let's consider x1 negation here, and this is x1. You see, there is no edge. This dotted line that I'm trying to draw, that it does not exist. Okay, so there is no edge between a literal and its negation. Okay, I think I just accidentally erased an edge. Let's try to put that back. Don't think so. Okay, so now let's go ahead. So this is how we construct this graph. Now, that's the important part, how we construct this graph, and that's a general way to construct the graph. What I've shown is just how to construct this graph using a particular example. Okay. So now, we have to show that this kind of transformation from phi to g is a reduction. That is what we have to show, that this transformation is a reduction. So we'll look at the graph again, but let's try to see how we prove this. So first, we have to prove that if phi has a satisfying assignment, g has a clique of size k. That's the first one direction. The other direction is g has a clique of size k, phi has a satisfying assignment. Now let's assume that phi has a satisfying assignment. That means that each clause CR, it contains at least one literal in it that is 1. Because any literal is actually and. So CR would look something like this. That is x1 or of x2 or of negation of x5. Something like this. That's what CR is going to look like. And CR has to be 1. Each clause has to be 1 because all these clauses are ANDed together. So each clause has to be 1. That is, at least one of these literals has to be 1. Now picking one true literal from each clause yields a set V prime of k vertices, because from each clause what we are going to do is we're going to pick one literal. So we're going to pick one literal here, maybe we're going to pick another literal here, so on and so forth. So you're going to pick literals. Therefore, from each clause you're going to pick one literal. Now if you pick a literal from each clause, you're going to have k vertices. So that's the first step to show that we can form a clique. Now, each of these vertices have to be connected to each other. Okay, that's the step that we have to show that V prime is a clique of size k. Now, any two vertices, when we pick any two vertices, now these two vertices are not in the same group; they are in different groups. So that part is already taken care of. Now, literals LIR and LIJS, these two literals corresponding to VIR and VJS, both map to 1. Okay, they both have to map to 1, and these two literals cannot be complements. Okay, they cannot be complements because otherwise they won't map to 1. Okay, and just by the way the graph is constructed, an edge always exists between VI and VJ, like VIR and VJS, if they are not complements of each other. Okay, this proves that there are k vertices in V prime, and together they form a clique. So far we have proved that if phi is satisfiable, G contains a clique of size k. Now we have to prove the other way. That is, suppose G has a clique of size k. Okay, so there's a clique V prime of size k, and we have to prove that the formula is satisfiable. Now, just by the construction, no edges in G connect vertices in the same triple. Okay, now therefore V prime should contain exactly one vertex per triple. Okay, these groups, the triple means these groups. You can only pick one vertex from each group. So we are going to pick k vertices, and k of them are going to be in different groups. Now, we know that V prime has a clique of size k, and we are trying to prove that phi is satisfiable. Now, what we can do is we can assign 1 to each literal LIR, okay, such that VIR is element of V prime. And why could we do this? This is possible because G contains no edges between a literal and its complement. So we know that V prime is a clique of size k. So all these vertices are connected to each other, and we could safely assign 1 to each of these vertices and say that that's the corresponding literals, because no edge, just by the construction of this graph, will exist between a literal and its complement. That link or that edge does not exist, so you could safely assign 1. Now, if you safely assign 1 to each of these literals, each of these literals lie in different clauses, and there is a 1 in each and every clause. Therefore, phi becomes satisfiable. Okay? So what we just proved is if G has a clique of size k, phi is satisfiable. So we did two things. First, what we did was we assumed that phi has a satisfying assignment, and we proved that the graph has a clique of size k. Then we assumed that the graph has a clique of size k, and we proved that phi is satisfiable. Okay? So therefore, we've proved both ways. This actually completes the reduction, and this proves that CLIQUE is NP complete. That's what this entire process proved. So what did we do? We first proved that CLIQUE lies in NP, and then we showed the reduction. Now, before I complete this video, I just want to talk about some important points. First thing that we have to understand is we took an instance of 3CN of SAT. Okay? We took an arbitrary instance of 3CN of SAT and reduced it to CLIQUE, and not the other way around. Okay? You cannot reduce the CLIQUE to 3CN of SAT to prove that CLIQUE is NP complete. We have to take 3CN of SAT, the well-known NP complete problem, and reduce it to CLIQUE. Okay? The second, we took an arbitrary instance, as I just mentioned. Now, we cannot take a specific instance of 3CN of SAT and reduce it to CLIQUE, because that specific instance may not be difficult to solve. So you have to take an arbitrary instance of 3CN of SAT and reduce it to CLIQUE. Now, when we did this reduction, we did the reduction of this mapping in a very bizarre way, or in a very specific way. So what we did was we showed that this arbitrary instance of 3CN of SAT is mapped to a very specific instance of CLIQUE. Okay? So and because we mapped it to a specific instance of CLIQUE, what we have shown here is that this specific instance of CLIQUE is hard. That's what we have shown here. Now, then how does it prove that CLIQUE in general is hard? Now, if you show that a specific instance is hard, that just means that the general problem is hard, because the specific problem that you're interested in is a case of this general problem of CLIQUE. Okay? So showing that a specific problem is hard just make sure that the general problem is hard. So with this, I'll complete this video. Thank you for watching.